Okay. Well, that's for my biology class. I don't know how well this is going to work. Okay. So I had moles and mass for my review, and honestly, at this point, if you don't know about moles and mass, you're probably not in a good position because we had this on our first exam, but I'm just now getting the video done. Mainly, I'll touch on a couple things at the end, but I'm kind of just going over problem set 4 for this review. So, yep, I would say if anyone has questions, you can ask me, but I probably don't know more of an answer than you do. Also, I'm alone in this Zoom meeting, so, yep, okay. Moles and mass. Okay, I actually just pulled these off of Dr. Mortensen's slides because they're helpful and pertain to this. So obviously we know 1 mole of anything is Avogadro's number, or 6.022 times 10 to the 23rd of anything. And there's actually a pretty good video that puts this into perspective, but I can't remember what it is. So I think I watched it in like my 10th grade chemistry class, but anyway. Yeah, so 1 mole of anything is always Avogadro's number. But the mass and the volume of whatever mole it is depends on what the actual substance is. So like a mole of water versus a mole of calcium is not going to be the same mass because their atomic weights are different. Okay. Oh yeah, and it's called molecular mass for like molecules, but formula mass for the ionic compounds. I don't think we need to know that, but just interesting. Okay, so the problem set. For this question, it wants us to calculate the average atomic mass. And to calculate the average atomic mass, we need to take the mass of the isotopes. I don't know if I can annotate on here. I'll annotate like one of them. Oh, I have it right here. Okay. So what we need to do is like I'll do the first one. So sulfur 32. Whoa, that's big. Sorry guys, I'm really bad at drawing on the computer. But so that's 31.9. So bad. Okay. 7, 2, 1. We multiply that by the percentage as a decimal of how naturally occurring it is in nature. So that's 0.9504. And I'm not exactly sure what that would be, and I don't really want to work it out on my calculator because that would waste time. But if you do that, you do that for S32, S33, S34, and 36, and you get the so you multiply the percentage as a decimal by the atomic mass, and you add all of them up. You can get the average atomic mass of, so here, right? So the 0.9504 times the 31.9721, and then you add them all up. And I'm pretty sure that equals like 58.962. AMU, but I can't remember if that's, okay, yeah. And then you should get the 32.06 if you took it all out all the way. And if you check on the periodic table, mine is super bright. It's 32.06, which is 32.1. So you did it right. Yay. Okay. Okay, so now for 1B, this is a little different. Sorry, this is the one that I was talking about for the 58.692. What you do for this one is you take the percentage and multiply it, obviously while it's in decimal form, multiply it by the AMU and do that for all of them, and then you add it up. And it's really similar question. They just have it written out more neatly for you because there's a lot more calculations that you have to do. And you should get, I got 58.692 for the answer. And yeah, okay, that's right. So once again, you're just gonna multiply this right here by this, but obviously in the decimal form, and then add them all up, and that gets you your atomic weight. Okay, so the number of protons determines the element. So I'm gonna move that down a little bit. Okay, so weight is not the defining property of the element. A lot of times we can remember the average atomic weights and determine, I mean, if you have like masses off the periodic table memorized, which I know I have a few from just using them over and over again. The number of protons determines the element, not the number of electrons or neutrons. The neutrons differing, but with the same number of protons, is what isotopes are. So let's see what they said. Okay. Yeah, the number of protons defines the element, not the atomic weight. And it is the mass of the neutrons that define the isotope, right? Anyway, if you're confused on this, I don't know how else to say it other than elements are determined by protons, neutrons of that element in different numbers determine the isotopes. So, and some are more naturally occurring than others. Okay, so for B, for this one, you just needed to multiply the mass by the natural abundance as a decimal again, and then add them all up. So yeah, I don't know. It should, yeah, the mass should be really similar because it's from the same place. Okay, cool. 3. Okay, this is an important concept to understand. So for this, it's super simple. All you have to do is look at the periodic table and see whichever one, like, so the 10 gives the mass number. So like 10B or 11B, which is boron, right? 10 grams or 11 grams per mole, or is AMU. So whichever one, so on the periodic table, boron is 10.81, and that's closer to 11 than it is to 10. So the boron would have, boron 11 would be closer than the boron 10. So that means that stable isotope is more abundant. Same, you just do it the same way for all of them. So lithium on the periodic table is 6.94, which is way closer to 7 than 6. So lithium 7 is the more common stable isotope. The nitrogen is 14.01. So 14 in, that isotope is a lot more abundant. Neon is 20.18. So so the neon 20 is going to be more common. Chlorine is 35.45, and that is closer to 35 than 37. So 35 should be, okay. So if that doesn't make sense, just remember that all you have to do is look at the periodic table and compare which isotope or what the average atomic mass is on the periodic table, and that will help you determine which isotope is more naturally abundant. Okay, number 4. Which of the highlighted elements below form monatomic ions with a charge of A + 1, B + 2, C? Okay, so the blue and the green are, is the green? Yeah, the blue and the green are both +1. So the way I remember this is it's super simple. I just count over. I kind of skip the transition metals. So I just go like 1, 2, 3, 4, 3, 2, 1. So up to 4, it's increasing in positive charge. And then after 4, you go back down to 3, 2, 1, and it's once again negative. So all of the alkali metals are going to be +1, and the blue is an alkali metal. 2, that is magnesium. Let me see. Yeah, I'm pretty sure that's magnesium. And that all the alkaline earth elements are going to be +2. C, okay, so that's a transition metal, and they're a little weird, but I'm pretty sure it's 3+ as well. I'm not certain, actually. The green one is silver, I'm pretty sure. Yeah, and silver, I just remember transition metals are weird, but silver doesn't change. And I just remember that it's got an 11, and so it's going to be a +1. It's in group 11, and so 1 and +1. So that's how I remember it. The red is going to be -2, so that'll be E. Because once again, it goes 1, 2, 3, 4, then -3, -2, -1, and that is oxygen. And also oxygen is like always -2, so remember that. And the purple one right here is in the, it's a halogen, and halogens are always going to be -1. So like 1, 2, 3, 4, 3, 2, 1. I actually have no idea if you can see my arrow, but if you can, that would be helpful. Okay, yeah. So here's a little bit. This is the explanation that was on the problem set key. Not my favorite explanation. I like how I think through it better, but my way may not make sense to anyone else. So, let's see. So for number 5, my explanation is probably not the best actually for this, but I just say, I'll read. Okay, I'll read this. So as we proceed across the row, number increases. Okay, alkaline. Okay, cool. So that's kind of what I said. I just think of it as it increases in positivity until group 15, where it starts to be negative because the electron I'm pretty sure this is because of the electron affinity. This answer might actually say that, but anyway, know your trends. Trends are super helpful, super important to remember in general. Yeah. I have a different periodic table, once again, colorful, that I have all the trends written on just to refresh and look at every so often if I can't remember. But understanding why the trends are like that will help you remember, what the trends actually are. Okay. Yeah. Okay, so define the mole. Mole is another way to measure. It is it makes everything more simple, because if we had everything in particles, that would be a ton, because that's 6.022 times 10 to the 23rd, which is obviously Avogadro's number. And it's just a more simple, a lot more concise, smaller way to measure. So yeah, it's a unit of measurement. Yeah. Okay. In principle, we could use the more familiar unit dozen. Okay, so moles are kind of like the chemistry dozen. A dozen still isn't really big enough. Yeah, it's too small of a unit for how many atoms or ions, everything we have in a mole. A mole is way bigger and super useful in chemistry. So, yep. Okay. All right. So more math. Great. For this one, so you need to recognize what you start with. If you had 1 mole of M&Ms, okay. So you want to start with your 1 mole of M&Ms. Let's see. This is gonna be so bad. Okay. 1 mole. Okay. And for every 1 mole of M&Ms, we have 6.022. Wow, this is terrible. Maybe I should type it. 6.02. Times 10 to the 23rd. Whoa. Okay. I don't know how to do this very well. Okay. Cool. Sorry guys, I've never this is before. Don't even know if anyone will actually watch it. Whoa. Okay. Why isn't this working? Okay. Per 1 mole. Then next we got, let's see, we have about 2.2 centimeters cubed. per 1 M&M. So if you see now we're getting to cancel out this, we're working on getting towards canceling out our 1 M&M. Okay, and we've got our so if you'll remember, you need to remember your SI like units. And we have like 1, then per 100 centimeters. Cubed. And then we'll have our okay, and if we do all that, then we'll see that we will have, how do I just draw again? Well, nope. Okay, I'm struggling technically. Okay, but once you do all that, your moles of your M&Ms right here cancel out, and your mole right here cancels out. This mole right here cancels with this mole, and we've got this number of atoms, and yeah, or not atoms, we have that many M&Ms. Anyway, and then centimeters cancel, our meters cancel, and then we have this kilometers. Oh my, wait. Guys, I don't even know. My brain is so dead. Okay. Anyway, I'm going to clear all those drawings. This maybe will make more sense. So we've got this, and we've got to multiply it by our size of the M&M, and then it tells us how much space the 1 M&M will take up. So it would need to be that big, which is huge. Okay, I'm not going to work this out, but all you have to do right here is take, you take this number, what you found from this problem, and you'll want to take the square root of it, or the cubed root of it, so you can just get the side of a box. Yeah, the size of the box. So yeah, and then up here you'll just compare it to all the things. So the length of the side of one of the box needs to be as long as Texas, just about. Okay, this stuff I think is more important than what we just did, so I'm sorry. I shouldn't have spent as much time on that. Right here, all you'll need to do is take the molar mass of carbon, which is 12.01 times 8, plus 1.01, which is the molar mass of hydrogen times 8, plus the molar mass of oxygen times 3, and add it up and that's the molar mass of the flavors, I guess. So that's 12.01 times 8 plus 1.01 times 8 plus 16 times 3, which is like 152 or something. Yeah. So this gives all of them, and you'll just do that for all of these, and it's super simple, straightforward. We've been having to do this all year at this point. I hope you know how to do it. Okay. Again, it's like the same thing. You'll just do like 12.01 times 12 plus 1.01 times 22 plus 16 times 11, and you add them all up and get your molar mass, and you'll do that for all of them. Super straightforward. Okay, now this is a little different, but if you have 1.5 moles of each substance, being able to figure out the number of oxygen. So we have the same moles of all of them. So really you just need to look at the moles of oxygen for each compound. So there's 11 here, 5 here, 6 here, 11. I don't know if we're supposed to look at, let's say look at B or C and A through H. Okay. So there's 3, 2, 1, 1, and then 11, 3, 5, and 6. So I think sucrose, yeah. Sucrose contains the most moles of oxygen. And you didn't have to do any calculations here because you had 1.5 moles of all of them. So you have the same number of moles of all of them. So that means the amount of oxygen is just based on, it's a 1-to-1 ratio. So then you just look at how many moles of oxygen per compound. Okay, so for 9, we need to see which one has, yeah, okay, the greater number of molecules. Okay, so for this one, it's which one has greater? Okay. Yeah, so whichever one has the smaller molar mass is going to have more atoms or molecules because you're dividing by a smaller number. So like the CO2 is 44.01 actually, but the nitrogen oxide is just going to be I think 30 or 30.01 maybe. And so since the nitrogen monoxide has a smaller molar mass, it's going to have more molecules because you're dividing by a smaller number. And that's just how all of them are. Which of the two would have greater number of ions? Okay. So for this one, it's kind of similar. Yeah, the same number of ions are produced then the smaller molar mass will result in a larger number of ions. Okay. Yeah, same thing because you're dividing by a smaller molar mass. And so like in question B though, when it has like Cl2, you need to know that when it dissolves, it's going to make 2 Cls and 1 Mg. So you need to remember that there are going to be 3 ions, not just 2 like NaBr or NaCl or KCl. But in the case of NaCl versus MgCl2, even though MgCl2 has more ions per molecule, it has a way bigger, it's like 40 grams per mole, almost bigger. And so you're dividing by a much larger number. So yeah. Okay, so this is going to be, okay, let me move this out of the way. All right, so here we just need to take our 8.1 grams and multiply it by the 0.035% manganese, because that is 8.1 grams is our coin, right? And we're trying to find the percent composition, sort of, well, it gives us the percent composition, but we need to find how many atoms of manganese. So in these types of problems, we just need to pretend, it's kind of arbitrary. We pretend that the percent is the number of grams. So right here, we use the 0.035% as grams. So we have 0.2835 grams of manganese per coin. And from there, you just go from grams to moles and moles to atoms. So it's pretty straightforward. Okay, 11, we do similar thing. So we need to read the question. Okay, yeah, so density, remember that I can't remember if we needed it for this problem, but for density, remember that, at least I think, gosh, now I'm second guessing myself, but the milliliters cubed, I'm pretty sure is the same. I mean, obviously it's volume, but it is no, centimeters cubed is it equals 1 milliliter. Yeah. So I don't know that we need it here, but it's useful to remember. Okay. So a common gem size used in wedding rings is about half a carat. The white diamond in my wedding ring is 0.536 carats, given the density. Okay. Okay, so we know that we have 0.536 carats. So what we need to do is go from carats to milligrams. So you'll put carats on top and multiply by 200 milligrams per carat. So the carats cancel, now your milligrams. Then you can go from milligrams to grams. And there's 1,000 milligrams per 1 gram. And then you'll want to divide by the molar mass of carbon, which is 12, because diamond is just a pure form of carbon, like it says in the question. And then you'll multiply by the number of atoms, and then and then you can get that. And if you just stop a step sooner, you can get the moles. So if you stop like right here, then you're at moles of carbon. Anyway, okay, so that is 3,106.75 carats. Okay. So all you need to do for this one is get the carats here, which is the 0.536, and divide 3,106.75 by the 0.536, and that's how many rings you could make them. Yeah. Yep. Okay. I have a feeling like that a question like this is going to be on the test. Okay, because I'm pretty sure we had a lab where we had to do this, same type of thing. So for this problem, you need to get the molar masses of both of them, and you just do that by adding up like 1 barium, 1 copper, 4 silicones, and 10 oxygens. You add them up on the periodic table. And I got I always think Han blue, like from Star Wars. Han blue to be 473.24 grams per mole, and the Egyptian blue to be 375.99 grams per mole. So the higher molar mass is going to be the Han blue, because literally all you're doing for this is adding up the values from the periodic table, and then you're subtracting the smaller one from the larger one. So you're subtracting the Egyptian blue molar mass from the Han blue molar mass, and so you get the molar masses, and it shows you how to do that here. And if you look at it, it's the exact same. Yeah, copper 1, silicon 4, oxygen 10. So the only difference is going to be between the barium and calcium. So yeah. And then this is the last problem, I'm pretty sure. All you have to do is if you have 10 grams of the Han blue and the Egyptian blue in both your hands, it should be the lighter one. I think the Egyptian blue. Yeah, so the Egyptian blue should have more moles of copper. I think it's easier to think about now that we've done a lot of percent composition problems, because if you think about the total amount, or if you think about the atomic weight of the copper over total, you get the percent composition, and it should be higher in the Egyptian blue one. But to solve the actual problem, you'll take 10 grams of that, the total Han blue, and get it into moles, and then per mole of the Han blue, we have 1 mole of copper atoms. And so anyway, there's fewer Han blue in the Egyptian blue. So I hope that was a good just run through, kind of remembering things, but here's a couple things to note. Isotopes are elements with different number of neutrons. It's the same element if it has the same number of protons. It's super important. There is normally one more that is more common than others, just because it's how nature is, and normally there's some that are a lot more common, which is why you get really close to whole numbers. And the atomic mass is average mass because of isotopes. So you're never going to like go in nature and grab out a carbon that has a mass of 12.01 grams or 12.011 grams. So remember to find the average atomic mass. We take the percent as a decimal and multiply it by its mass, and then we add them all up and we get the average atomic mass that we get from the periodic table. Super important to remember. Right, and this is what I was saying a second ago. There's a 0% chance that you'll pull out an atom with the exact mass from the periodic table because they're averages of the isotopes. Oh, and 1 atomic mass unit is, it used to be equal to 1 proton, but then they changed it to like 1/16 or something of carbon 12. Anyway, I can't remember exactly. But 1 AMU is equal to 1.66 times 10 to the minus 24 grams. AMUs are super not useful in lab because they are so small. So we use grams, and we have our grams to mole conversions that we get from the periodic table. Yeah, and I think this is the last slide. The molar mass in grams per 1 is the mass in grams per 1 mole of substance, which is what you get from the periodic table. And down here is just, it shows like how you go from grams to moles to particles. But if you wanted to stop right after the grams to moles, then you can have your number of moles. So anyway, I hope this was helpful. I'm not sure if it was. I don't even know if anyone really will go and watch it, because I don't think I really need help with the moles and mass stuff because we've just been doing so much based on it. But yeah, that's all I've got, and good luck everyone on the final, and hopefully it's not too hard. All right.